Hey there, Math Hoppers. In this video lesson, we are going to look at inverse functions and relations. So inverse relationships simply undo one another. Two relations or functions are inverses of one another if for each value ab, the other function or relation contains the value ba. And this is what I mean. We have two relations here, m and n. M is defined as 1, 3, 2, 5, 1, negative 3, and 2, negative 5. Clearly not a function because the inputs 1 and 2 both go to more than one output, right? Function for each and every x value can only go to one and only one y value. 1 goes to 3 and negative 3, 2 goes to 5 and negative 5, and that's a no-no. So n, where m has 1, 3, n has the 0.31. Where m has 2, 5, n has the 0.52. I bet you can see the pattern here. Where m has 1, negative 3, n has negative 3, 1. And where m has 2, negative 5, n has negative 5, 2. So we can see that the inputs and the outputs, or the x and y values, have been switched here. So let's look at inverse functions, because really what we're concerned about are functions and inverse functions. And before we do that, let's take a little review of what a function is and look at some traits that we know about functions. So if we consider the function f of x equals 3x plus 1, it's simply a linear function. We've worked with these a long time. Let's define it for a few values. So f of 1 is 3 times 1 plus 1, or 4. F of 2 is 3 times 2 plus 1, or 7. F of 3 is 3 times 3 plus 1, or 10. And f of 4 is 3 times 4 plus 1, or 13. So those values that we put into the function, 1, 2, 3, and 4, those are values in the domain. The domain, remember, is the set of all x values for a function. And when we put those values in, the values 4, 7, 10, and 13 that we got out, those were not only outputs, but those were values in the range, because the range is the set of all y values to a function. And remember, when we first learned functions, you may recall seeing function machines or mapping diagrams, which would show you the relationship between the domain and range of a function. So let's look at one of those. The mapping diagrams would look like this. Sometimes they would say input up here and output up here, or x and y, or x and f of x if you had already learned function notation, right? F of x tells you this is a function whose variable is x. But either way, they told you for the input 1, the output would be 4. Or for the domain value of 2, the corresponding range value would be 7. Or for the x value of 3, the corresponding y value would be 10. Or for the x value of 4, the corresponding f of x value would be 13, right? So the point of the mapping diagram was to show us how to get from the domain value to the corresponding range value. Well, now the question is, do we have a way to get from the range back to the domain? We know how to get from the domain to the range. We've been doing it all of our algebraic careers, so to speak. And the answer, of course, is yes. I wouldn't ask it if the answer was no, right? So we do have a way to get from the range back to the domain, and it is by using inverse functions. So what are inverse functions? Well, a little more review still. Remember that f of x equals 3x plus 1. F of x is just the outputs of the function, and they are the y values. Remember way back when we used to just write y equals 3x plus 1, and then we learned all about functions, and we learned the vertical line test, and we learned that if every input had one and only one output, it was a function. And so instead of writing y, we wrote f of x, which said, hey, this relationship is a function whose variable is x. It was just a way of writing y equals with more information. Like you were telling somebody, hey, if you're going to do the vertical line test, don't bother. I already did it. This thing's a function. So remember for this that f of x and y are interchangeable. All right? When we apply the function, we put in x values, we get out y values, right? Because we have a function, if you think about this, we have a function that's solved for y in terms of x. Look at that. We have y equals 3x plus 1, where our y values change depending on what we put in for x. So when we apply the inverse function, we are putting in y values, we're putting in range values, and we're getting out domain values from that original function. Now the symbol for the inverse function is this guy. We call this the inverse of f, or the inverse function. I almost never say f to the negative 1 because it's not an exponent. It literally has nothing to do with exponents. I don't know why they picked it, but this is the universal symbol for inverse. When you learn matrices, the inverse matrix will be A with this little -1 superscript. Okay, notice I really try hard not to call it an exponent. It freaks people out. It has nothing to do with an exponent. It is simply the universal symbol for inverse. Like, negative exponents weren't bad enough, so we had to bring them up where they had no business being. All right, let's look at some properties. And I apologize for all the heavy math here, but we're going to explain it in real English. So f of x and the inverse of x are inverses only if for f of a equals b, there is an inverse of b equals a. And that makes sense from what we already know. The function takes the input and spits out the output, takes the domain, spits out the range. The inverse takes the range, spits out the domain. All right? So what does this all really mean? Well, I'm going to explain it in plain English. And by plain English, I am going to use equations, but it's going to be okay. All right, we have two functions here. We have 2x plus 4 and its inverse, 1/2 x minus 2. I realize you have to take my word for it that these are inverses because we haven't yet learned how to take the inverse, but we're getting there. So trust me, these are inverses. I want to show you something about them. So if we take f of x and we solve for f of 2, that means I want to know what the value is when we put 2 in for x. So f of 2 is 2 times 2 plus 4, or 4 plus 4, or 8. So knowing what we do about inverses, if the function has an input of 2 that corresponds to an output of 8, what else should be true? Well, shouldn't it be true that our inverse function would take 8 and spit out 2? It would take the range and spit out the domain? Based on everything I've told you, yes. So let's see if it's true. So the inverse of 8 is 1/2 times 8 minus 2. 1/2 of 8 is 4. 4 minus 2 is 2. So look at that. The inverse took the range and spit out the corresponding domain value. All right, to determine the inverse of a function, we are going to replace f of x with y. Remember, they're interchangeable. Not really doing anything there, but we want to see x and y values. We are then going to switch the x and y values, right? We'll switch x and y in the actual equation. Very key, because that is switching the domain and range, which is what the relationship between the function and its inverse are. And then we will solve for y. This will be a lot easier if we just do it, so let's just do it. Given f of x equals x cubed minus 1, let's determine the inverse function for x. F of x equals x cubed minus 1. Our first step is the easiest. Replace f of x with y. Done. Y equals x cubed minus 1. Remember, I can't solve anything yet. I have to switch x and y. We need to switch that domain and range. This is kind of the key of all of it. So we get x equals y cubed minus 1. And now we're just going to solve this sucker like we've solved every other equation in our algebraic careers thus far. So solve for y. We have to get rid of that -1. How do we do that? Add 1 to both sides. We've got x plus 1 equals y cubed. Do not forget that taking the cube root is the opposite of cubing. Take the cube root of both sides. The cube root of y cubed is just y. Remember, these are inverses of one another, so they undo each other. So we get y equals the cube root of the quantity x plus 1. So we have this equation solved for y, but it's actually a really special relationship. It's the inverse of the function we started with, but we won't know that until we label it. So what we're going to do is replace y with our inverse symbol. And so we say the inverse function in terms of x is the cube root of x plus 1. Not too bad. All right, now I'm going to throw the graph at you, but we're going to go through it step by step. So this is the graph of a function and its inverse, but not just any function. It's the functions we just looked at. So this is x cubed minus 1, and the inverse, the cube root of x plus 1. Okay, so let's label it. There's our original function, the cube root function. There we are, vertically shifted down 1. This is the cube root function. Looks kind of familiar. And there is our cube root function. And there's another line there. And that line is to help show the relationship between these two functions. This line right here is the y equals x line. And these two graphs are reflected over the line y equals x. Okay, so let's see why. A function and its inverse are reflections over that line y equals x. But why? Well, let's think about what y equals x really means. Y equals x means for every x input you get back y, right? Well, the function f of x maps 0 to -1 for this, right? Our function gave us 0, -1 right here. So that's x to y. So the inverse better do y to x. So I better see -1 to 0. So -1, 0 is on the inverse. So it makes sense that they're reflected over that y equals x. What's the first thing we did? We switched x and y. All right, so don't let the graphs of these fool you. I used to see some people, sometimes my kids would fold the paper on a diagonal to graph the inverse. Yeah, that totally works because that diagonal was the y equals x line. All right, not all functions have inverses. Let's look at this guy. We're not going to do too much with it. It's just kind of a visual to get us into this. So this is a quadratic, okay? A quadratic does not have an inverse that's also a function. Because look, if I reflect this thing over y equals x, I get this purple graph. That purple graph is not a function because look at my vertical lines. They are hitting 2 spots each input. Each input has 2 different outputs. That's a no-no. We can't have it. All right? So what we say is f of x here, this quadratic, is not invertible. So that's a new word. Let's talk about it. All right. When the inverse of a function is also a function, the original function is said to be invertible. Great. Like we didn't have enough math vocabulary. Okay? We use a vertical line test to see if a graph is a function. We've talked about that several times. So we use a horizontal line test to determine if the function is invertible. So we use a horizontal line test to determine if the inverse of that function is also a function. Let's look at what I mean. Here is a nice cubic function. It's actually x cubed minus 1. We've worked a lot with it today. And if we did the vertical line test, we know this is a function, but it's labeled f of x, so we don't have to. But let's do the horizontal line test. Horizontal line test, yes. Crosses the graph once at each place. So the inverse of this function, f of x, will also be a function. So f of x is invertible. Let's look at something that's not. Even though we just saw a parabola, let's look at something else. G of x. I can call it g of x. It is a function. But when I do the horizontal line test, look at that. I have 4 points that cross that horizontal line. The horizontal line that just disappeared, but nonetheless, 4 points on that horizontal line. So the inverse of g of x will not be a function. G of x is not invertible. Okay? So another new term, if a function is invertible. So if a function has an inverse that's also a function, it is 1-to-1, meaning all y values are matched to exactly one x value. Now, I like to say all y values are matched to exactly one x value. I've seen textbooks say all x values are matched to one y value and all y values matched to one x value. But guess what? All x values being matched to one y value is the definition of a function. So you don't have to repeat that, okay? It's 1-to-1 because all of these y values come down to just one x value. All right, last thing, we have to be able to verify inverses. And this is great because on your test, if you're solving for the inverse of a function and you have a little extra time, you can verify if you got it right. All right, so two functions, f of x and g of x, are inverses of one another if and only if f of g of x and g of f of x both equal x. Look at that. We just learned composition functions and now they're coming in handy. All right, let's do an example. F of x equals 4x squared, g of x equals 1/2 times the square root of x. Are they inverses of one another? Verify algebraically. Guess what, guys? When you see this question on your test, you can't just say yes or no. Even if you're right, you're not going to get hardly any credit. I bet you don't get any credit. You've got to show that you know composition functions are used. All right, so f of g of x means take the f function, so take 4x squared, and instead of x squared, we put, or instead of x, we put 1/2 square root of x, right? We put in g. So f of g of x means take this function g and put it in for x. So 4 times something squared, that something is now g. 1/2 times the square root of x. When we do that, 1/2 times the square root of x squared, by the way. When we do that, if we square 1/2, we get 1/4. If we square square root, they cancel each other, we just get x. So let's look at that. We get 4 times 1/4 x. All right, 4's cancel, right? 4 over 1 times 1 over 4 is just 1. So we get x. So f of g of x equals x. We're halfway there. Don't stop here and say, yeah, they're inverses. You got to check the other one. G of f of x means take the g function, so take 1/2 times the square root of x, and instead of x, put in the f function. So put in 4x squared. So 1/2, oh, and this squared shouldn't be here. Just pretend that's not here. 1/2 times the square root of 4x squared, right? G doesn't have a square there. So 1/2 times the square root of 4x squared. Let's see if I remove that from my next. I did remove it from my next. So the square root of 4 is 2. The square root of x squared is x. 1/2 didn't get touched. 1/2 times 2x, my 2's cancel. And I get 1 times x, or x. So g of f of x is also x. So yes, these are inverses of one another. All right, there are no examples at the end of this lesson because this lesson was already long enough. Functions, relations, inverses, verifying inverses, graphs of inverses, it's a lot to take in. If you have questions when you're doing your homework, when you're doing a quiz in this module, remember you should be subscribed to our YouTube channel. It exists for you. When you are confused, send us those problems. We will make a custom video solution to help you out. Until next time, Math Hoppers, take it easy.